We are rolling, and hi there, people. Welcome to another video. I don't really have a script, but I do have a tons of integrals for you guys. Today, I'm starting a new series, kind of a three-part series where I'll derive the standard trigonometric integrals. It's better if I just show you guys, what I mean. We got the whole gang, x squared plus a squared and x squared minus a squared and a squared minus x squared. The whole gang, we're gonna derive them. We're gonna solve some examples and we're gonna see how they are tickled. So this is a three-part series, and this is just number one. Okay, the first video. So it's gonna be nice. We're gonna do the x squared plus a squared gang today, and I guess let's just get started. Let's just get started. And over here, we have the first one. We have our first integral. I have my notes right here. I will refer to them if I need to. I'll try not to, but yeah, it is what it is. Okay, let us see how we do this. Again, the name has trigonometry in it, so that means we're going to be doing some trigonometry here as well. It's gonna be pretty nice, but again, there are some things you guys need to know before you start deriving and like solving this. Namely, you gotta know how to do the basic trigonometry, all right? Identities. You gotta know how to do partial fractions. That is very important. Partial fraction decomposition, basically, and you gotta know how to do some completing the squares. You gotta know that is taught in algebra, intermediate algebra. And most of the calculus is hard because we are bad at algebra. It's not the calculus, it's the algebra. So if you guys know the algebra, you are good to go. So great, that's about it. And there will be a few common integrals that you will need to know. So over the whole series, we're going to see what they are, and just like figure it out on the way, I guess, just like how we do in life. So let us start with the first one. All right, great, sounds awesome. We've got the integral of 1 over x squared plus a squared with respect to dx. So how are we supposed to go about thinking? How are we supposed to go about solving this? Okay, is there any way we can make this easier? Any algebraic manipulations we can make to, maybe simplify this a bit? And yes, again, we can. We absolutely can. We can, divide the whole denominator by x squared. We can do that. So if we do that, I'm going to remove the integral for now. I'm just going to focus on the fraction over here. We got this one, right? So we can divide the whole denominator by x squared. And to make things, to keep things equal, we got to multiply the numerator of the denominator now by a square, because it's just we are doing some algebra, right? We're just manipulating the things so we can cancel them out. Everything is just the same. These are equivalent. So sorry, I mean the integral is not. I mean this and the original fraction, they are equal. All right. So great. So what does that mean? What does that mean? That we can just take this minor fraction, you can say, and let me write it here. We can do it like this. This will be the first one. Let me put the bracket. And these a squares, let me do that, cancel that. Yeah. So these a squares are going to get cancelled because this is just two different fractions, right? So that's what we will get. We will get this thing plus 1 and the a square over here. Great. So again, you can just put a bracket around here as well and erase these squares, right? And but essentially this is like the x by a squared. That's it. So we got this one. So we can put the integral sign back again, right? And over to dx. Great. We know that this a thingy is just a constant, so we can factor this out, right? Absolutely we can. So that means we got 1 over a squared times the integral of we have this whole x by a squared plus 1 dx over here. Great. Now if you have done some differentiation, you might have came across this one. This is very similar to the inverse, the derivative of the inverse trigonometric tangent. So arctan, right? Inverse trig, inverse tangent, tangent inverse, whatever. Okay, so we got this one. And just to not go into just calculus and mugging up all the formulas, why don't we take a geometrical approach and try to solve it the good old Pythagorean way, right? Good old Pythagorean way. So let me just draw a triangle, all right? Just a right angle triangle, good old, our favorite right angle triangles that help us figure out some stuff. And why don't we make a simple substitution? Why don't we make a simple substitution that, let me draw a line over here. Yes. Why don't we do a simple substitution that x by a is just tangent of, say, some angle phi. I like phi's, they are really cool. I don't like thetas. Okay, so this is the simple substitution. And if we have to translate this to a right angle triangle, this one is a right angle triangle, by the way, what do we get? We get something like, imagine this to be the phi, okay? That means the perpendicular, that's this one is here, x, and the base, that's there, is here, okay? So x over a. This is by the definition of a tangent of an angle, all right? Great. That means we can figure out the hypotenuse as well, which will be just x squared plus a squared, and we put square root over there. Great. We know this exists. This is true, right? Okay, fine. Great. So we can put this tangent thingy over there, right? But before that, we need to find dx as well, because now we're talking in terms of phi's. So if we're supposed to integrate in terms of x's, that wouldn't work. That is blasphemy. So why don't we do some more algebra right here? Let's do x equals a tangent of phi. Absolutely true, correct. We just cross multiply this thing here. Okay. And why don't we differentiate both terms by with respect to phi? Okay, so dx d phi will get the constant back, and that's how it works, the differentiation rules. Yeah, you gotta know, you gotta be able to differentiate things, right? Both in life and in maths. Okay, so what is the derivative, first derivative of tangent? That's secant squared phi. Great. So we can move this d phi over here. Great, because we know how to cross multiply things, don't we? Great. So we have this one, and now we can plug both of these in, this substitution and this substitution. Let me draw that in a different color to distinguish between things. Let's take the good brown color. Not so good, but all right. So we can substitute this back into our good old integral. So let me go 1 over a squared, this thing, and 1 over tangent squared phi plus 1. Let me, okay, great. Okay, and dx, we got a secant square of phi d phi. Great, amazing. Well, we can factor this, because this is like being multiplied, not being added. We can just factor this a out over here. Again, I should use different colors, right? So factor this a out. And what else do we see? Do we see some other simplification? Yes, this thing over here. What do we know about tangent square of any angle plus 1? That equals to just secant square of phi, because that's one of the common trigonometric identities, right? So great, amazing. We can substitute that and take out the a from the multiple thingy. Yeah, great. And we got good old nothingness. And yes, secant squared phi d phi. Great, amazing. Oh, I'm sorry, you guys weren't able to see that. Yeah, so we got this thing over here, and we can just cancel these out. And isn't that amazing? Canceling things out, that feels nice, right? do not cancel me, by the way. Yes. So, and we got 1 over a times d phi. Amazing. So we can just integrate just phi, which is, we know is phi, simple as that. So let us do that. A times phi plus c. But we're not done yet because we gotta figure it out. Like, what are we talking about, right? What phi? What is phi? We don't know what phi is, but we do actually. We do. We made a substitution. This one, right? We made a substitution. We can just take that. Okay, let me write it again. X pi equals tangent of phi, and we can just switch things up a bit. We can swap it. Okay, we can find the inverse of tangent. That means phi equals the tangent inverse or inverse tangent or arctan, if you will, of x by a. That is the same as differently written arctan and x by a. Great. So we know that this whole thingy, we know like 1 over x squared plus a dx equals to nothing but 1 over a, that's this thing right over here, 1 over a arctan x by a plus c. We don't forget the c, do we? And that matches with my note. So there we go. We have derived the whole thing. We can see what this means and we can apply them into formulas now. Let me draw a box over here. Great, amazing. So let me recheck this whole derivation. All right, let me see if we've made any errors, because we gotta check our work constantly so that we don't mess up, right? So am I sure of this whole step? Oh, okay. Am I sure of this whole algebraic shebang over here? Yes, we are. This can be done. That's how things have been done for ages. Okay. Probably not the best way to phrase it. Yeah. Okay. So that is amazing. We can factor out this a squared. Great. And that means a is a constant, so we can just factor it out from the integral rules, and we've got this thing over here. And we have done some good old linking, linking to our Pythagorean triangle, or a right angle triangle, if you will. So this thing is going to be pretty handy over in this whole x squared plus a squared gang. This substitution, this whole tangent thingy is going to be very, very handy. So keep that in mind. Am I sure of this one? Absolutely. We can do that. We can relate it to a arbitrary angle phi. So that is absolutely true. This thing is true. Cross multiplication and finding the derivative is also true. So great, amazing. And now we just substituted the whole thing and use the secant square of phi, the identity, to just simplify the things a lot more, and just finding the thingy, then back substituting. Yeah, because we know we made this substitution, so we are back substituting phi over here, and to get our final result, final integrand. So there we go. We are done with the derivations. So let us do some examples, right? Let's just plug and chug. The first example is this one, integral of 1 over x squared plus 4. But before I do it, I want you to try first. So I hope you've got your pencils or pens or whatever, fountain pens. I don't know what you guys use. I like to just use a ballpoint pen because that's fast, right? I like fountain pens as well, but okay, we're diverting from the topic. All right, so let us try to find what the x's are, what the a's are. Okay, so clearly this is x squared, and 4 is just 2 squared. So we know that a is just 2. Great. So can we just plug and chug into this formula? Absolutely, we can. So this will be just equal to, okay, blue is fine. 1 over a, which is 1 over 2, arctan or tan inverse, whatever you want, x over a, which is again 2 plus c. Great. Again, you can also just divide the whole thing by 4 and multiply it by 4, bring the 4 out, and x plus 1, substitute x by 4 is it for x by 2 to be tan phi, and do it that way. Same old the substitution that we made just here, you can do it here as well if you like have forgotten this formula, because that's what it's about, right? It's not about memorizing for the formula, it's about using things, right? Using the things we've already learned to solve new problems. So you can definitely use that. As always, do not memorize, try it, find it yourself, and then do it. Okay, then do it. Of course, in competitive exams and board exams, it's handy to memorize it, and you're gonna do that anyway. I know, because I'm doing it. So it is what it is. So make a distinction, right? We can move over to the next problem. This is the second example. So amazing. Let's try this one as well, but pause the video and try it yourself first. Okay. So what is this? What? Yeah. Okay. So we have something weird over here. X plus 2 squared instead of just x squared. Hmm. Uh, that's not good, is it? But just kidding. It's good enough, bro. It's just good enough because we can just take u to be x plus 2. Simple as that. We don't need any formulas and stuff. We just pick an arbitrary variable u to be x plus 2, and then that means we can just do it like that. Okay, let me do that. Let me go for this one. Let me show you what I mean. This is just u squared plus 49 dx. But you said we have u over here, but we have x's over here. So that ain't gonna work out. So what we are gonna do is take the derivative of this whole expression, both side by dx. So du by dx is just nothing but we got 1 over here, and the constant will go to 0. So this is the thingy, and that means we have du equal to dx. So we can erase this dx over here and replace this with du, and it will still work. It is all equivalent, and we're all good. We're all set. So we can just use the formula, the arctan thingy here. But of course, we have to find out what the square root of 49 is. If you don't know what the square root of 49 is, uh, find it out, I guess. Find it out, and you gotta know. Okay, you gotta know. All right, I'm not going to sugarcoat it anymore. You gotta know. It's 7, or is it? Either way, let's just do it. So 1 over 7, and arctan of u over 7. Again, this is a, u over a plus c. But we're not done yet, because we have taken this arbitrary variable u, and we're gonna export our answer back in terms of x, right? So 1 over 7, then we got arctan. We can just easily use inverse tangent. They're all similar. Equal, I mean, same thing. So x plus 2, we're going to replace u back to what it was, 7 plus c, and that is our answer. Amazing. So I hope you have learned at least what this integral means and how you can use it. You can still definitely use our good old this buddy, three-sided buddy here to find the answer if you think you've forgotten the formula, because it's not about the formula, it's about using tools, right? So again, we have used formulas, but yeah, either way. Okay, so let's move on to the next member of the gang, which is this one over here. And okay, do I have it? Yeah, we have it. All right, let's do it. Great. I'm opening my notes, and let's do it. It's going to be amazing. Can we do the same algebraic manipulation over here? Dividing the a squared, dividing by a squared and finding out the thingy. Yes, again, we will do that. Do the same thing over here as well. Okay, great, amazing. So let me focus on just the polynomial now, right? So we have got x squared plus a squared, and we can just put on the thingy over here. And again, we're gonna divide. And let me give the equal sign this time, because I gotta make it visible, right? So, okay, so we're gonna divide both sides by a squared and multiply by a square so that things are conserved. Yes. and that is equal to, we can like bring this thing out, because if you just square root something, is going to be a. So I hope you know that a, amazing. And we've got x by a squared plus 1 over here, the same thing that we had in the previous integral. So okay, and now we can put on the integral signs. Great. So we will have this a outside the integral, because it is a constant, and inside we'll have the same thing, x over a squared plus 1 dx. Again, we'll use our good old three-sided buddy. Let me just copy this thing over from over here and paste it, because we're going to need it again and again and again. So this thing, amazing. And you know what we substituted x by a with? Do you remember what? We did it for tangent of this random ass angle phi. So we're going to do the same thing over here as well. So let me, okay. So x by a equals tangent of phi. Great. And we can cross multiply here. I should probably not use this brown color right now. Probably yellow. All right. Great. Because that matches with the triangle. Okay, so we can just as well find the derivative of this thing, because we'll need that again and again and again. So secant square of x, sorry, not x, phi, d phi. Okay, great. Okay, so what are we up to this time? We'll surely substitute it back in the equation. So let's try it. Let's try doing that. We've got a, and let me make a line over here actually, so that we don't forget that. Okay, should work. Great. So a, we're gonna substitute back to tangent squared of phi plus 1, and we have a secant squared x, not x, phi, d phi. Great. All right, so we can factor this a out, because it's being multiplied, not being added. So that's one of the integral rules, a squared. And look what we have here. This is again the same identity that we used last time. So this is tan squared phi plus 1, that equals to secant squared of phi. So we're gonna replace this with secant squared. And we've got secant squared over here, d phi. So we can remove the square root. Definitely we can. So that equals to a squared secant cube of phi d phi. And here's what I was talking here's what I meant when I was talking about standard trigonometric integrals. This is one of them, and I'm not going to go in depth of how it's found out, because you gotta know how to do by parts and stuff. So I'm just gonna write what this integral is. So make sure to do that by yourself, by the way. So do not rely on me for everything, right? I hope you're not. So what do we have here? This equals to, let me write the a square over here. This equals to the not the natural log, but half of the secant phi tangent of phi. I always forget this actually. It's like one of the harder formulas, like integrals, to remember. And we got a minus over here, I think. No, it's a plus. Great, amazing. So half the natural log of secant of phi plus tangent of phi. And we're going to close the absolute thingy and plus c. Yeah. So this is what we have so far. This thing over here is this thing over there. So great. It's a long integral. Make sure you know how to find that out. If you'd like, just comment down below. I'll make a video on how to find the integral of this one. Okay, but we're not going to do that in this video, right? Okay, great. Amazing. So we can just plug and chug, like distribute a squared over here. So a squared times the secant squared, not plus, but multiply. Okay. Tangent phi plus a squared by 2 natural log of secant phi plus tangent of phi plus c. Now, we're not done yet because we're still in phi mode. We don't want to be in phi mode. We want to be in x mode, right? So we're going to use this triangle over here to figure out what we already know what tangent is. Definitely. Where's the blue one? Yeah, we know this one. Absolutely. But we do not know the secant. What is the secant? Secant of phi? How do you find that out? Well, we know this thingy angle. We know the sides. Absolutely. And then we can use the basic trigonometric definitions to solve for secant. And what is secant? It's just reciprocal of cosine, right? So what's the cosine? Let me find that. Let me do that over here. So cosine of phi is nothing but the base by the hypotenuse. So that equals to a over x squared plus a squared. So secant would be the opposite, the reciprocal of this. So secant phi is just x squared plus a squared over a. Okay, great. I feel nice. Yes, great. So we can just substitute that back here. Yeah, okay, great. Let me do that in this color. We got this thing. Right. X squared plus a times a, and we know the tangent, and tangent is just x over a because we know we made that substitution, right? And over here we have a squared 2 and natural log. Natural logs are very nice. I like him a lot. Again, we're gonna substitute this thing back again. X squared plus a plus x over a, and we're gonna close this absolute value over here. Great. And you can pretty much see that this a is multiplied with this a, which makes them a squared, and it's going to cancel this a squared out. But in this case, we don't see that because it's just being added. So we're going to write it again one last time and we'll be done. So we have what here? I'm going to write it in a different form because I find that easy to memorize. So we have this thing over here, a squared over 2 natural log of x plus this thing over a plus c. Okay, so we finally have the integrand of this bad boy over here, and it's crazy. Okay, because you see this square root of x squared plus a squared, we see that over here. Let me draw that in red. Over here and over there as well. So it's pretty easy to remember. Just put it over there and put the x on the right side. On the right side. And if you notice, some books have omitted this fraction, this part over here, because it's just, if you use the logarithmic properties, this is just x plus this thing minus natural log of a this thing. So this is just a constant. It's not, oh sorry, if you, sorry about that, you were not, my camera just hid the thingy. So this is just, this whole thing equals to this thing. So as I was saying, this part is just a constant, and that is integrated into this plus c over here that we write usually. So some books omit this, but again, for the sake of purity, mathematical purity, I guess, I like to keep this. So do whatever you want. It won't make a difference. They both are same because this is a constant and this is a constant. It all gets integrated later. What matters is you have this part, and this part. You don't want to miss them out. All right. So just constant. If it's a constant, we just tag in the plus c. That's what the plus c is for, right? Unless we have an initial condition, that's going to change things. So, all right. So this is great. We are done with the whole integral. Whew. So let us move over to do some examples. All right. How long has it been? 30 minutes. Wow. Okay, great. So let us just use the formula. Okay. We know this thing. We know what the x is. Sorry, x and a are. Again, square root of 47. Ah, square root of 47. That is supposed to be plus minus 7 because that's how square roots work. No. I made a mistake. Sorry. A squared is 49. So if you just square root both sides, that is going to be, this is supposed to be the absolute value, the definition of absolute value. So it's not going to be minus, but the plus of the square root 49. So that's going to be 7 because again, you know that real numbers do not have negative squares. This is squared and it's being rooted. So you're going to get the positive value over here. Again, a little bit of real analysis, I guess. Okay, we know this one. A is 7, definitely, and x is x. So we can just plug and chug. We know the formula. The formula says that this integral equals to 1 over x times, we know this thing repeats again. So x plus 49. And we know a squared. We don't even need to find the a except for the natural logarithm part. So this is going to be just 49 over 2 times natural log of x plus thing which repeats itself. Not talking about exponentials. And we got 7 over here and plus c. Wow, great. So again, we can choose to omit this part out because it's going to be added afterwards there only. So great. We can move over to this problem. Again, I forgot to mention it, but you should try it yourself because it's amazing. I'm gonna drink some water till you do it. So water is nice. It's pretty cool, you know. All right, let's continue with our math ventures. So what do we see here? We don't see a explicit x or explicit a. Things are a bit weird over here. So when things go weird, we know what to do. We know that we are supposed to do some algebraic manipulation. So let's give our brains some fuel, I guess. I don't know, and let's do it. Okay. So, we know we want the form to be something like this one, right? We know we want the x's and the a's to be isolated. At least we want the x to be isolated. So what can we do? Can we divide this thingy by 25 and multiply it by 25, of course? The same thingy. We know how it works, right? So that this becomes 1 and we isolate the x. So yeah, we're going to do that. Great, absolutely. Of course, there are multiple ways to solve a problem. So if you find a more efficient way to do something, then you know what to do. Just comment it out and I'm going to see it and I'm going to give you some nice YouTube hearts, okay? So, all right, let's move on to the problem. Okay, we're going to divide the whole thing. Let's focus on the polynomial now, not the integral. So dividing the whole thing by 25 and multiplying it by 25. So we're going to extend this over here. And I should have done this over here. Sorry. Great. So we'll have, because this is just 5 square, we're going to take out a 5 because it's being rooted. Rooted, that's what I call the square root thingy. So 5. And then over here we have 13 over 25 and this is just being cancelled. Let me do that in red. Great. So plus x squared. That's what we have. Great. We know the thingy and we can just plug this in into the integral. So the integral is just 5 over here because constant integral rules. Yes, we know that that happens. That is true. So, okay, let me draw the 5, like write the 5 in a better way, I guess. Okay. Then over here, we can write this thing in a different way just to give ourselves some peace. Okay, we have the same thing, not the weirder thing. Okay, because reversing these tends to mess with our brains, right? So let's not mess with our brains, not too much at least. We gotta mess with our brains enough. Okay, so 5 over there, amazing. Now we can find out the a's. This is just a squared, we know, right? This is just a squared because that's the form. So what is a? If a squared is 13 over 25, we can just find the positive square root of the both sides and find a to be square root of 13 over 5. This is a. Great, amazing. So we can just plug it in into our formula, I guess. All right. Let me do that over here because this has more space. So let me draw a line like this. Let me use the brown color. Great. So we know that this is just, okay, sorry about that. This is just 5 and we're integrating the thingy. So let me draw a square bracket. And we know that this is just half and the thing will repeat itself. So x times x squared plus 13 over 25. Great. And we'll use the x squared we have and we'll have to, okay, so x squared, this is 13 over 25 divided by 2. That means the 25 will get pushed to the bottom. So we'll get 25 times 2 and we're going to do a natural log of x plus the thing that will repeat itself by a. What is a? This thing over here. 13 over 5 plus c. Now we can do some more algebraic manipulation. Bring this 5 in. So 5 over 2 x times the thing that will repeat itself. Again, this is x squared. Great. And then this is 13 times 5 and 25 over 2. You know, this is going to get cancelled. So this is just 5 and we'll have a 10 over here. Sorry about the messy handwriting, but I mean, it's all scratch work. That's how it's going to be in exam halls, at least for me. So, all right, so natural log, we're going to bring the 5 over there because this is being reciprocaled, if you know what I mean. So 5 and then multiplied by x plus this thing that will repeat itself. And in the bottom, we have a nice squared root of 13. Do not forget the plus c, definitely. So we have the whole answer right here. Please forgive me for this one. I'm lazy, you know. I don't want to work too much. So we have got this one. Again, we can omit this. Forget it. Just omit this whole part. We don't need it. Then we don't have to do more algebraic manipulation because it's just going to get added into the C. But because of mathematical purity, we have it right here. So we got the thingy. Great. We are done with the square root of x squared plus a squared. And that is amazing, right? I hope, again, if you have any questions, any queries, please post it down in the comments and or any means you have, I guess, because there are going to be links in the description where you can reach me and ask me anything, whatever you want. In anything. Okay, let's just move on to the next integral because we have a good one over here. It's just the younger sibling of the last one, and things are going to get cancelled quite a bit. It's going to be easy to derive and easy to solve. So great. Again, same. We're gonna do the same algebraic manipulation. That's bringing the a out over here and multiplying the thingy. So I'm just gonna cut the steps and just tell you what's it's going to be because you already know how it goes, right? So just focusing on the polynomial. So we got a and then we got a by x squared plus 1. Great. This a is going to be outside. So let's just bring this out and just draw an integral and draw a 1 over the a. Great. And this is the idea. Again, you're going to substitute x by a with tangent of phi and things are going to be great. So let's do that. Again, we know that dx is going to be a over secant, not over, times secant square of phi d phi. So amazing. We're going to substitute that here. Sorry. Okay, this is just tangent squared of phi. So we're just gonna write this thing over here, and here we have a times secant squared of this one times d phi. So we know this a is going to get out and these are going to get cancelled. So amazing job. Again, this is not supposed to be x squared. Sorry about that, because we have the square root over here, right? Oh, sorry, I erased it. We have the square root over here, though. This part is secant square of phi, but we're squaring it, so it is going to be just secant of phi. So great. That means this part and one exponent of the secant square phi are also going to get cancelled. So great. Let me write that over here. This is, as I said, a's are going to get cancelled, and we are just left with just the lonely secant phi d phi. Again, this is what I meant when I was talking about standard trigonometric integrals. You're gonna need to know what is the integral of secant of phi is as well. And let me tell you, this is also very intuitive to derive. Of course, it takes some ingenuity, I should say, to do it, but let me just tell you the answer. We're not going to derive it again. You are free to comment down below if you want the answer. I mean, the whole video to find the derivative of both secant cube of phi and or any angle, secant phi. Okay, so please feel free to do that, and feel free to try it yourself as well, because that's where learning begins, right? Again, let me tell you, this is just going to be natural log of secant phi plus tangent of phi. That's it. This is it. Okay, this is just as simple as it goes. This is the integrand of this integral. Okay, so we can substitute it back for the secant and the tangents. We know what the secant and tangent are from the previous derivation, so we're just going to do that. So it's going to be natural log of we'll have the secant first, so x squared plus a squared over a and plus x over a, and we're going to close the modulus here, and then we're gonna do this thing. Just write it in a different way to be able to memorize it better. So great, awesome, and we have the final result over here. So that's easy, pretty easy to derive. You just needed to substitute the tangent thingy that we did, and that's all. And of course, this part is important. This part is important. Again, a lot of integrals are important. For example, tangent phi d phi. This is very important. Sine, cosine, cotangent, I mean, and cosecant. They're all very important. You should be able to find the integral, okay? Even if they are a bit weird. So we've got our example. Again, try it yourself first without me holding your hand and doing so. All right, so what do we got here? We got the a squared, that is 10. So that means we know that a is going to be just root of 10, right? Square root of 10. So let's just plug and chug into this formula right over here. We just need this one. Okay, great, amazing, amazing, amazing. Easy, very easy to solve, right? Natural log of, we've got x plus the thing that will repeat itself. You notice this pattern? This thing is just, let me go back a couple of days, a couple of slides, I guess. Yeah, this thing is just this thing from the previous integral, just this thing. That's why I said it's like the younger sibling of this one. So this is just the thing. So it is pretty easy to memorize, because this is just the um, numerator, I guess, and the integral that we are doing is the reciprocal of that one. So it flips and reduces. It reduces. You can think of it that way. to memorize it, I guess. Pick whatever you want. So plus 10, and we've got our root 10 over here because that's a, and we're going to close this thingy, plus 6 plus c, and we are done. Great, amazing. So yeah, let's move on to the next example. This one is a bit tricky. I want you to try it. Please pause the video. Please try it. It's a bit interesting. All right. We're going to have to do something different compared to our other examples. So, yeah, I cannot wait for you to try it. I hope you can do it because we're going to do some hint completing the squares. Please do it. Okay. We're going to start in 3, 2, 1. All right. So let us try it ourselves. This is completely different because it's a quadratic equation, quadratic polynomial, not the thing we were expecting, right? Not the thing we were expecting. So we gotta find a way to simplify it a bit. So how can we do that? How can we do that? Yes, we can complete the square to find particular squares, combination of squares, that's what the method says. So let's just focus on the polynomial, not even the root. Let's just draw a line over here. Draw a line over here. And let's try to do some algebra. Okay, algebra. This is all about algebra, not even about calculus. This is not even a calculus video, man. This is just algebra. Of course, we are doing calculus. So it is calculus video. Again, I'm rambling over here. Let us try to solve this thing. So how does the completing the square method works? Well, for any general a x squared, let's forget the a for now because we don't have any a over here. That's the easier version of completing the square, because if we have a's, then things get a bit messy. So let's just focus on the normal a squared plus b square bx plus c version of this thingy. What happens is that you find something called b minus 2 and then square it and then do something like this. I'm very bad at teaching this because this is something that is hard to teach actually. So we have this one, and we're going to add this thingy. Wait, let me wipe this, and let me wipe this as well, and me teach completing the square here. I should not, because I did not think teach the other methods, but this one I think it's pretty important. Okay, we got any general a x squared plus bx plus c. What we're going to do is we're going to find a part, a missing puzzle piece. Okay, that is b squared b by 2 b over 2 squared. That's what we're gonna do. So, and we're gonna do, we're gonna add it over here, and we've got plus c over here, and we're gonna subtract it over here, because this means that we're not changing anything with the whole expression, with the whole equation. We're just adding something and subtracting something. So that means everything is conserved. We're cool. But this gives us a squared. How? Because if you can compute this, if you reverse engineer this part, this will be x plus b by 2 squared. Yeah, that's what it's going to be. Again, you just expand this and find it out yourself, man. Just expand this and you'll find that this works. This will be equal to this one. All right, this part. And then over here we'll have c minus b squared by this thing, and we can just compute this. This is a normal number. Does not matter if it's a square or not. We can just, if it's not a square, we can just square root it, and that will give us a cleaner form in this polynomial. So great. We will be able to just use a u sub for this one and find the integrand for this problem. So let us just trying doing that. I'm gonna wipe this thingy because we don't need that right now. Let's try doing this for our equation. I don't know if I made sense for the past 2-3 minutes. I hope I did, but if I did not, just feel free to watch some other video or comment down below if you want me to make a better explanation on this topic. Okay, so let us try doing it here again. It's just muscle memory now. So what is b? B is 6, so b by 2 will be 3, and we're supposed to square it and add it and subtract it. All right, too many steps. Let me write it out. So this is minus 3 squared, and again we have, sorry, this should be addition. Great, and minus 3 squared. And this thing becomes x plus 3 squared. And over here we have minus 7, minus 9, and that effectively is what? Minus 16. Great. We have a squared. So x plus 3 squared minus 16. Great. So this thing over here equals x plus 3 whole squared minus 16. So we can find the thingy very easily now. So that's what we were doing. All right. This is what completing the square gives us. It makes our life easier. Of course, we did not really use it when we needed to in like grade 7, 6. I don't know when it's taught, but again, okay, let's focus on this one. Great. We have this thing. We can just pick a u, and u will be this one to make things easy. So dx will be du because it's just a linear. So du will be dx. I'm doing it in my head, so please don't get confused. Please try to do it. Okay, I'm gonna make things clear. All right. Just picking u to be x plus 3. If we differentiate both parts, this is just 1, this thing, and the constant will be constant. So du will be dx. Simple as that. So great, amazing. Let's do that over here. So u squared minus 16 du. And we know the formula to this one, don't we? This is just natural log of, we have u over here. Yes, because we are just doing u. No, not x's, because we are u. We are in the u mode, not x mode. Right. And plus, sorry, I forgot the square roots. Damn. Okay, so u plus minus. Okay, minus. Yes, and the square root of 16, which is 4, plus c. We're not done yet because we're still in the u mode. We need to go back to the x mode over here. So that x has to be what? X plus 3, right? So x plus 3 plus, we got x plus 3 squared minus 16 over 4 and plus c. Amazing. Okay, sorry. Yeah. Okay, great. Amazing. We found the result. This is the integral. Again, if you found any errors in this video, anything, just comment it out. I'll do my best to edit them or do it whatever, make clarification in the comments at least. So okay, amazing. We are done with the last one. Okay, we are done with 1 over square root of x squared plus a squared. I hope you learned something. I hope you were able to do the problems again. This is time where I part the way. We have a problem set PDF in the description, so you can check that out. Practice a lot of problems because that's how you learn more. And click this here over here. I guess this side, this thing over here. Click the video for the next integral type. That's x squared minus a squared. So it's going to be amazing. Check the new video definitely, and join my Discord server because it's amazing. We have people studying over there. We have accountability thingies. You can post stuff and make friends and find study guys and resources and just meet like-minded people. It's amazing. So I hope you learned some things from this video. Again, if you have any requests, please comment down below and subscribe to the channel, hit the bell notification, and yada yada, whatever YouTubers say in the last outro. Either way, take care of yourself, and I'm gonna meet you in the next one. Okay, I should probably turn on this camera, no? Because yeah. Take care of yourself. All right, stay frosty, and see ya in the next one. Okay.